All right. So last time we talked about we started chapter 19, that is about acids and bases. We introduced the theories that is defining the definition of acids and bases, and those are the named after their scientists who discover them. And we talked about Arrhenius acids and bases. Then we talked about the Bronsted and Lowry, and then we talked also about the Lewis acids and bases. Based on what we have said last time, that Arrhenius is the one, the definition of acids and bases. Acids are the one which can produce H plus whenever they ionizes in solution, and the base is the one that produces hydroxide ion. Also, after that, we introduced the Bronsted and Lowry, which is a little bit more general and includes other material, and that is defining the acid as the hydrogen ion donor, and base is the hydrogen ion acceptor. Then came the Gilbert Lewis, who introduced a more general definition that includes also more material. That defines the acid as the ferroelectron acceptor, and the base is the one that is donate these two electrons. And so the base basically the one which has the lone pairs, and acid is the one which is accepting those lone pairs. Today we are moving on with the hydrogen ion and acidity. So we're going to talk about the acidity of solution, and also how to become acidic, or to be acidic, or to be basic. Here's one of the questions that we usually have, which is the question in a picture. As you can see, we have this golden fish, that is in a fish tank. And the question is, what factors do we need to control in order to have the fish stay healthy in a water and live for longer? Of course, based on the idea that we agreed upon last time, that the questions are always related to the topic that we're discussing. Apparently, we're talking about the pH has to be controlled, because depending on whether the type of the fish, whether it's coming from seawater or coming from a freshwater type of fish, then we use different types of pH. Okay, the objectives for today are we're gonna see the relationship between the concentrations of the H plus and the concentration of the hydroxide ion. Of course, this one here with the brackets, this type is read as the concentration. So when you see something like that, when you read this one, you say concentration of H plus. And the same thing applies to this one. This is the concentration of OH minus. Okay, so what is the relationship between the two concentrations, how they are related, whether they are directly or inversely proportional, and how can we determine them, and all that will be discussed today. Then how can we classify the solutions as being neutral, being acidic, or being basic using the pH? Using the pH value. The third objective, of course, we're going to talk about the methods of used usually in measuring the pH of solution, which is mainly using pH meter or using indicators like a litmus paper that you guys are all maybe aware of before. All right, now going on to the relationship between the hydrogen ion and the hydroxide ion in solution. Um, we have to consider something that is already known, which is the fact that the water molecules are, first of all, highly polar. When we say highly polar, this يعني because when we say they are highly polar, this means that the OH bond is with the positive, partial positive here and partial negative here is barely, this is very polar, which means that the electrons are already pulled too much toward the oxygen. That is one fact. And the other fact is the fact that they are in continuous motion and they collide with each other. So when we have pure water, usually the water molecules, one of the water molecules, and here's another, they collide with each other. They will interact with each other in an ionization reaction, where one of them is going to act as an acid and the other one is going to act as a base. Now, the one which is acting as an acid, according to the Bronsted-Lowry, is the one which will produce or will donate, donate the H plus. So this one, let's say, will lose an H plus and donate it to that one. So one of them is going to form a hydronamine, which is usually, it is an H plus, but we know that H plus does not exist as a free ion, but rather than that, it is existing as the hydronamine, H3O plus. And of course, the one which is given off the H plus will remain as OH minus. So with this kind of a reaction, which is usually called a self-ionization reaction, which means that the water molecules will ionize themselves, not as, typical ionization reaction is like, for example, HCl. HCl plus H2O, they produce H3O plus Cl minus. In this case, the water is ionizing the hydrochloric acid. But in our case here, we're talking about self-ionization, where a water molecule is ionizing another water molecule in a reaction that is known as self. Now, if you want to write it in a much simpler way, we can write it this way, which is a water molecule is divided into H plus and OH minus. That is what the self-ionization is about. Okay, so one water molecule is donating an H plus and the other one is receiving that. Now, they found that according to the measurements, that when we have something like this, which is a reaction like that, having the water self-ionized, or water molecules divided into ionizes into H plus and OH minus, they found that the concentration of the H plus is equal to 10 to the minus 17 molar. And also they found that the concentration of the hydroxide ion is equal to the 10 to the minus 7 molar as well. So they are equal, and that is whenever we have a pure water at 25 degrees C. All right, that is very important, because if we have impure water, then this whole thing will be different. It's not, the concentration is not going to be the same as 1 times 10 to the minus 7 molar anymore. Okay, so that will produce what we call a neutral solution, since both of them are the same. So when we have the concentration of H plus is equal to the concentration of OH minus, okay, and to the concentration of OH minus, and that is equal to 1 times 10 to the minus 7 molar. All right, that is what we call a neutral solution. They are equal, and each one of them is equal 10 to the minus 7. Now, there's one principle that was discovered by the French scientist, which is Le Chatelier principle, they call it Le Chatelier. Okay, that is French. Le Chatelier's principle calls for the following. Now, I want you to remember one thing before, which is the fact that if you look at this reaction over here, okay, this is a reaction that is in equilibrium. You see these arrows are going back and forth. Yes, one of them is longer than the other, which means that the reaction is pushed toward the water molecule rather than the ions. But that is a kind of equilibrium, we call it. Equilibrium means that the two reactions are occurring. The forward and the backward reaction can occur at any time. Okay. So what is Le Chatelier principles calls for? It says that whenever we have a system in equilibrium and one of the component has, or the concentration of one of the component has increased, then that will form a stress on the system in the equilibrium system, and the system will react in a way to minimize that kind of stress. Yani, this means that when we have something like this, okay, we have the water is ionizes into H plus and OH minus. Let's say that, we have this reaction in equilibrium. All right, so the equilibrium exists in there. So we have the water, H plus and OH minus, all of them exist at the same time. Now, when we add, let's assume that we add to this some hydrochloric acid, HCl, or H plus, let's say. We increase the acid. So that will make the H plus becomes more than the OH minus. And that is what kind of a stress that we're talking about. So the equilibrium system will act in a way to minimize that by moving the reaction toward this side. Okay, in order for the extra H plus to react and reduce it and bring it back to where it was like the OH minus. Okay. And if we add also a hydroxide ion more, that also will create a stress and the system will react accordingly. So according to Le Chatelier principles, adding either hydrogen ion or hydroxide ion to the aqueous solution is a stress in the system. In response to that stress, the equilibrium will shift toward the formation of water. So adding either acid or base will shift the reaction toward the water. The concentration of other ion will decrease. In other words, if we add H plus, we expect the reaction to go back to the water molecule, and that will consume more hydroxide ion, and hydroxide ion will decrease. Okay, so increasing the H plus will definitely need or will push the OH minus to decrease. And also the same thing applies to the hydroxide ion. Adding more hydroxide ion will push the reaction to move toward the backward, and that will make the hydrogen ion less. And this way we can conclude that in any aqueous solution, when the concentration of H plus increases, OH decreases. Likewise, when H plus decreases, OH minus increases. What does that mean? That the relationship between the concentration of H plus and OH minus is inversely proportional. As one of them is increasing, the other one has to decrease with the same amount in order to keep the equilibrium in place. This is what Le Chatelier principle is about. So considering the fact that each one of them is equal to the 10 to the minus 7 in pure water at 25, then if you multiply 1 times 10 to the minus 7 times 1 10 to the minus 7, that's equal to 10 to the minus 14. So the multiplication of the two concentration is equal to a constant, and that constant is equal to the 10 to the minus 14. Now, this 10 to the minus 14 is now called Kw, and that is the ion product constant for water, they call it. Okay, so the product of the two concentrations of the hydrogen ion and the hydroxide ion water is called the ion product constant for water, and that is Kw. So the new equation that we are introducing to you today now is the is this one, which is stating that Kw, which is equal to 10 to the minus 14, is equal to the concentration of H plus times the concentration of H minus. All right. So again, having such an equation, if we tell you what is, or we provide you with the H plus concentration, then you should be able to calculate the concentration of H minus, right? And determine the other one. So if the H plus is going to be higher than the OH minus, this means that the solution with the greater one is going to be acidic solution. And in that case, the concentration of H plus is greater than 10 to the minus 7. If we add to the solution some hydroxide ion, that will increase the concentration of hydroxide ion to more than 1 times 10 to the minus 7, and that will make the solution basic. If we don't add anything and we have a pure water, then both of them are equal to each other, and that is 10 to the minus 7. In that case, you know, they will be called a neutral solution. So we have three types of solutions. Either we have a neutral one where the concentrations of both H plus and OH minus are equal, or we have the H plus is higher than the OH minus, which means that the solution is acidic, or the basic solution will happen when we have the H plus is less than the OH minus. That is basic solution. As I said, using that equation, which is state that the Kw is equal to the 10 to the minus 14, and at the same time, it is equal to the concentration of H plus times the concentration of H minus. If we provide you with one of them, you can determine the other one. And that's why we can solve this example using that kind of equation. If the H plus in aqueous solution, now this is the concentration of H plus that is provided, 10 to the minus 5, which means that it is greater or less than 10 to the minus 7. Now, is the when we say that the concentration of H plus is 1 times 10 to the minus 5, is this greater or less than 10 to the minus 7? That's a question. It is less. How did you know that it is less? عشانها minus 5 يعني? But this is a negative, so it will be, it is actually more, because when we have the 10 to the minus 1, that means that the higher the number, the lower the concentration. Anyways, what is the concentration of H minus in that case? So we use this equation, which is Kw is equal to 1 times 10 to the minus 14. All right, and that is equal to the concentration of H plus times the concentration of H minus, and that is equal to 1 times 10 to the minus 5 times the concentration of H minus, and that is still equal to 1 times 10 to the minus 14. When you rearrange the equation for OH minus, then the answer will be 10 to the minus 14 divided by 1 times 10 to the minus 5, which is in that case equal 10 to the minus 9. Okay, so in that case, I'm not asking about the concentration of OH minus, yeah, Daniel. My question was whether 10 to the minus 5 is greater or 10 to the minus 7 is greater. All right, so the H plus is greater than 10 to the minus 7, and that's why the solution is acidic. When we do resolve the equation for, or rearrange the equation for OH minus, then it is equal to Kw divided by the concentration of H plus, and that is substituting the number, it will be equal to 1 times 10 to the minus 9. Which means again that the concentration of H plus is greater than 10 to the minus 7, and the concentration of the OH minus is less than 10 to the minus 7, and that is again indicating that the solution is acidic. Now, continue using these kind of things, which is 10 to the minus. What about if it is a fraction, like something like 3.5 times 10 to the minus 14 or 10 to the minus 7, using the molarities to indicate or to find out whether the solution is acidic or basic is not practical. For that reason, they included or they introduced the concept of the pH, which is a scale from 1 to 14 that can be used to indicate the acidity or to decide whether we have an acidic or basic solution. From 0 to 7, that is acidic, and from 7 to 14, that is basic, and at 7 itself, that is a neutral solution. And that is coming again from the concentrations of the H plus and the concentration of OH minus. All right. Now, how to determine the pH using the H plus concentration? We can use this equation in front of you, which states that the pH of any solution is equal to the negative logarithm of the H plus concentration. So if you have, or if you know the concentration of H plus, which you can, of course, using the KW equation, you can determine it. Then in that case, using your calculator, or I will show you in a minute that you can also use your mathematical or mathematics knowledge in order to determine the pH or to solve this equation, which is the negative log. So in pure water, again, we know that the concentration of H plus is equal to 10 to the minus 7. Now, using that in the negative log, that will give you the negative log of 1 is 0, and log of 10 to the minus 7 is negative 7, so that will give you a pH of 7. So when we have a pure water, and when we have the concentration of H plus is equal to 1 times 10 to the minus 7, then the pH in that case is equal to 7. And if the OH minus is equal to the OH minus, then is equal to 10 to the minus 7. That is a basic solution. So a solution with a pH of less than 7 is acidic. So the higher the concentration of H plus, the lower the pH is. Okay, so when we have higher concentration of H plus, of OH minus, H plus concentration higher than 10 to the minus 7, then that means that the pH will be less, and that is from 0 to 1. And pH 7 is a neutral, and above that, this is a basic solution. So this is the range of pHs, as you already know that, which is starting from 1 to 14. We have from 1 to 7, and from 7 to 14, where we have the acidic and basic solutions. Okay. Now, going back again to the same question that we asked you at the beginning of an aquarium, a pH of is a very important factor and for the survival of your fish. It depending again on whether this fish is coming from fresh water or coming from a seawater. It seems that the salts in the seawater tank is either a pH slightly basic, so if it is coming from a fresh water, it has to be acidic. So that is the answer of the question about what controlling the factors. Calculating the pH, as I said, the best thing, and the most people, what they are doing, they're using the calculator. But if it is not available and you have only whole numbers like 1 times 10 to the minus 7, then as I said, negative log of that is equal to the negative log of 1. Logarithm of 1 is always 0. So that will make it, the answer is equal to the logarithm of the 10 to the minus something. 10 to the minus 5, this means that it is equal to negative 5 because it is the negative logarithm of H plus, so that will give you negative is positive, and that is equal to 5. So we can calculate the pH using our knowledge like this, a solution with H plus equal 10 to the minus 2, for example, the pH is 2. How do we know that? Because negative log of a concentration of H plus, negative log of 1 times 10 to the minus 2, which is equal to the negative log of 1 plus the negative log of 10 to the minus 2. Negative log of 10 to the minus 2 is minus 2, and the log of 1 is equal to 0, and this way. But if it is a number like this one, then that will become difficult, and in that case, we can use the calculator. What is the pH of a solution with a hydrogen ion concentration of 4.2 times 10 to the minus 7, 10 to the minus 10? We know that the answer will be very close to 10, but we don't know how much exactly. So first of all, we write the equation which states that the pH is equal to the negative logarithm of H plus. And in that case, we're using the calculator. That will lead into 9.38. Okay, so having a pH of 9.38, this is acidic or basic? That is a basic solution because the pH is above 7. If it is above 7, then in that case it is basic. Well, that is already stated that. We can do the backward, which is if we have the pHs known, then we can determine the hydrogen ion concentration or the H plus concentration by also using the antilog, as they say in the calculator. So you have to make sure from now on that you know how to use the logarithm of a number in your calculator and how to do the antilog in your calculator as well, because that's the only way you can determine that. So from 6.35 pH, that is acidic. So we expect the solution to be around 10 to the minus 7, but rather we can determine that, and that is 4.5 10 to the minus 7. Okay. طيب, if the OH solution is, if you know the OH minus solution, you can also find the pH, right? Because from the OH concentration of hydroxide ion, you can determine the H plus concentration using the KW equation, and from that you can determine the pH. So here's an example on that, which is what is the pH of a solution if the hydroxide ion concentration is 4 times 10 to the minus 11. Now remember that the pH is equal to the negative logarithm log of the concentration of H plus. So first of all, we need to find the H plus concentration using the KW is equal to the concentration of H plus times the concentration of H minus, and is equal to 10 to the minus 14. That is the first thing. Then we substitute. Okay, so here we go. Using the KW, we can determine the concentration of H plus is determined here from this equation, which is equal to 2.5 10 to the minus 4. And in that case, all what you need to do is to use this one in the negative logarithm of the concentration of H plus, and that will lead to 3.6. Okay, so either if we provide you with the H plus concentration or the OH minus concentration, you should be able to determine the pH using the KW relationship between the two. Measuring the pH, this is the last topic that we're discussing today, and that is very easy and straightforward, and that is based on whether we can use an indicators or a pH meter. pH meter, that's an instrumental thing. I mean, there's an instrument called a pH meter, which has an electrode, and that electrode can be dipped in any solution or a soil or any other thing that you want to measure the pH, and the reader or the screen will show you what is the pH. Now, the other part, which is using acid-base indicators, there are some, as we mentioned last time, some compounds that when they interact with H plus, they can, and OH minus, they can change their color. Now, here HI indicator, this is an acidic form. Now, the indicator could have an acidic form or a basic form. HIN means an indicator with H in there. If it ionizes into H plus and ion minus, then this is the base form of the indicator. Okay, so keep this equation in your mind, that if we have, and remember Le Chatelier principle, if we have more of H plus, which means that the solution is acidic, then the equilibrium will be shifted into that direction. So in that case, the HIN will be dominant in that case. Okay, is dominant at pH with high pH, and the HIN is dominant in the low pH. Let me repeat this again so you guys can understand it again. So if we have an indicator that is added to our solution, now the color will depend on which form is available. Those indicators, they change their color when we go from the acidic to the basic forms. Now, this is the acidic form, and that is the basic form. Now, if the H plus concentration is higher, which means that the pH is lower, then in that case, the equilibrium will be shifted into this direction. So HIN will be dominant, will be higher, and that is where we have the color is equivalent to the acidic one. And if the H plus is lower, then the equilibrium will go into that side. Or if the OH minus is higher, then in that case, we have the basic form in there, and that is the color is different. Okay, the change from the domination of, or dominating acid form to the dominating base form occurs when we have a narrow range about the pH. So in other words, we have, for each indicator, we have a range of a pH where the color is changing. This is, for example, the phenolphthalein, the very famous one. As you can see, it is changing from colorless in the acidic form into purple in the basic form, and many other like the methyl red, for example. This is also another famous one. Bromo thymol blue, which is this one, also changing color from yellow to blue whenever we have the solution changing from acidic to basic thing. So we can use that piece of paper, which is an indicator strip, is a piece of paper or plastic that has been soaked in an indicator and then dried. So we're talking about a piece of paper like that, which is having, it's made from paper or plastic, but it contains the indicator in it. So we can dip that solution or that paper in our solution, and based on the range of colors that we have, we can determine the pH. One other natural thing of, the pH is these two flowers are the same type, they are the same quality, but depending on the soil where they are planted, in acidic soil, they are blue, and in basic soil, they are, red, like what you can see, or, pale red. Okay, so depending on the flowers of the soil, we can determine that. The pH meter, as I said, this is a very old one, but there are some digital ones these days where you have the electrode that is dipped in the soil or dipped in any solution, and then you can read the pH from here. Now, this is an analog pH meter, which is still showing the color, but we can have one of those digital ones where it's showing the number, exactly what is the pH. So in conclusion of this section, we have learned mainly three things. First of all, the relationship between the H plus and OH minus is inversely proportional, and we have this equation which is called Kw, that is equal 10 to the minus 14, and it is equal to the H plus concentration times the OH minus concentration. We can use that equation to determine any concentration that we like if we provided with the other one. The second piece of information that we learned today is about the pH that the pH is equal to the negative logarithm of H plus. We can use the calculator to determine that. And also, the last thing we talk about is measuring the pH either by an indicator paper or by using the pH meter. Okay, so that's what we have today. Inshallah, on Tuesday, we will continue with that, chapter 19, and we will consider section number 3. Do you guys have any questions before we close this session? Any questions or concerns? All right. So we'll speak to you again, inshallah, on Tuesday. All right.